Have you ever wondered what oxidation states are? What does it mean? What are they used for? How do you calculate them? And how do you compare them with each other? If you've wondered about any of those things, you're certainly not alone and you're in the right place. Those are the things we're going to be talking about in today's episode. Welcome back to the Chemistry Made Simple podcast. I'm your host, Matthew Macario. It's great to see you back here. And if you're new here, if this is your first time, let me introduce myself. I'm Matthew Macario. I'm a tutor, coach and mentor for chemistry students just like you. If you're looking for the clear explanations of the chemistry principles, for example, oxidation states, then you're in the right place. Hit subscribe or follow because this is the start of that journey to clarity. Now, as I mentioned in this episode, I'm going to talk about oxidation states. I'm going to clarify everything about them. What do they even mean? What are they for? How do you calculate them? What are the rules for them too? And why am I doing that? Well, because it comes up, it's going to come up in your exams time and time again. You need to know this stuff, so let's get on with it. So let's start with, what are oxidation states? Well, these are a number that is given to each atom within a compound or within an ion. It's a number that tells you how many electrons have been lost or gained, either completely or by sharing in covalent bonding, compared to the elemental state, the uncombined state of each atom there. And that number, it could be positive, it could be negative, it can be zero. It's usually a whole number, an integer, but there are examples where it's not, and we will come across one of those in today's episode as well. For simple ions, oxidation states tell you how many electrons have been lost or gained. By simple ions, I'm talking about ions where whether it has just one atom that is either lost or gained electrons, or more than one atom, but all the atoms are of the same element. Now, for atoms that are in covalent bonds, whether they're part of a complex ion or whether they're part of a compound, the oxidation state is giving you an indication of how the electrons in the atoms are being used in those bonds and how they're being distributed in those bonds. One of the key things about oxidation states is that they're numbers. In fact, it's sometimes known as oxidation numbers. You may have heard or read oxidation states being referred to as oxidation numbers, and that's fine. It makes sense because it is always a number. So how do we calculate them? Well, there are some rules to guide you, to help you work it out and to help you understand them, of course. And it's also true that many elements have common oxidation states. There are a few elements that have only one oxidation state other than their elemental oxidation state. And knowing those, learning those is really going to help you to calculate and work out the oxidation states for those atoms, those elements that have oxidation states that are less predictable. So what are those rules? Well, the first one is that all elements, when they're in their elemental state, when they're uncombined with something else, when they're not an ion, they're not part of a compound, when they are truly in their elemental state, they have an oxidation state of zero. For a compound, the individual atoms within the compound will have oxidation states that are not zero, but if you added up the oxidation states for all the atoms present, the total is zero for a neutral compound. For an ion, again, each of the atoms present will have its own oxidation state that's not zero. And then when you add them up, you total the oxidation states for all the atoms within an ion, the total will match whatever the charge is on the ion. For example, the nitrate ion, NO3-, the charge is 1-, so the total of the oxidation state of the one nitrogen atom and the three oxygen atoms, total of those will give -1. The total of those oxidation states is -1. Now I mentioned that there's elements whose atoms outside of their elemental state form only one other oxidation state, and we need to look at those. So remember that all these, in fact, all elements in their elemental state have oxidation state zero, so we're talking about the situation where it's not in its elemental state. Let's start with group 1. So group 1 will only form a +1 oxidation state. We're talking about lithium, sodium, potassium, and so on. they will only form a +1 oxidation state when they are not in their elemental metallic form. Group 2 elements, beryllium, calcium, magnesium, and so on, only form the +2 oxidation state when they're not in their elemental metallic form. And following on, aluminium in group 3, that only forms the +3 oxidation state, but it's just aluminium out of group 3 that we can say has a fixed oxidation state. So those are the metals that have a fixed oxidation state. There is also one element that's not a metal that has only one oxidation state, and that's fluorine. Fluorine, when it's not in its elemental form, only forms the -1 oxidation state. So these are important to know and remember. These are your absolute guarantees of what oxidation state is an element on this list in. There are also a number of elements that have more than one oxidation state, but have one oxidation state that they're almost always in. Let's have a look at which ones they are. Again, just like every other element, when these are in their elemental state, they have oxidation state 0. So we're just talking about when they are forming ions, when they are part of a compound. So hydrogen usually forms the +1 oxidation state. You probably have come across H+ quite a lot. It gets mentioned a lot in chemistry. It's the H+ ion that you get when you have an acid. But hydrogen can form a -1 ion and therefore a -1 oxidation state. It's not particularly common, but it can do so, and you need to be aware of it. When does it do that? Well, it forms metal hydrides or metal hydride ions. Chlorine always forms a -1 oxidation state. As a simple ion, it forms a chloride ion, but also in its covalent compounds and covalent ions, it forms -1 with exceptions. The exceptions are where it is combined with fluorine or oxygen. Fluorine and oxygen happen to be the only elements that are more electronegative than chlorine, and therefore they can take electrons away from chlorine. They can oxidize chlorine so that it has a different oxidation state. Speaking of oxygen, oxygen usually forms a -2 oxidation state. You'll see that with the O2- ion, for example, but also most of its covalent compounds or covalent ions, it forms the -2 ion. But it can form other oxidation states. It can form a -1 oxidation state, and you'll see that in peroxide compounds. There's a very unusual ion called the superoxide, which has a -1/2 oxidation state. And oxygen can also form a +2 oxidation state, and that's when it's in a compound with fluorine, OF2. Fluorine is the most electronegative element, and although oxygen is the next most electronegative, fluorine still trumps it. It still will oxidize oxygen and form that compound, making oxygen have a positive oxidation state, i.e. it's in a situation where it's been oxidized relative to its elemental state. So learn these oxidation states. These will really help you to be able to calculate the oxidation states of other elements that they may be in combination with. Okay, let's consider some examples. We're going to work out the oxidation state of nitrogen in NH3 in ammonia, and then the oxidation state of nitrogen in the nitrate ion NO3-. We'll start with nitrogen in ammonia, and let's consider those rules we talked about. So the first rule we need to consider is that ammonia is a neutral compound, and therefore the overall oxidation states of the nitrogen and the 3 hydrogens will add up to 0. The second thing we need to consider is what are the common oxidation states of the other things that are in ammonia. So in this case, we just have hydrogen. We mentioned that hydrogen forms a +1 oxidation state. It does form a -1 oxidation state in metal hydrides, but this isn't a metal hydride, so it's the +1 oxidation state of hydrogen that we need to consider. There are 3 hydrogens, so the oxidation state of each is +1. Totaling those together, we have 3 pluses. The nitrogen must have oxidation state of -3, because when totaled with the +1 of each of the 3 hydrogens will give us a total of 0. And that's what we need because ammonia is a neutral compound. Let's think about nitrogen behaving differently. So nitrogen in the nitrate ion, NO3-. This has 1 nitrogen, 3 oxygens, and the overall charge is 1-, it's negative. First rule we need to consider is that when we add the oxidation states of everything together, they must equal the total of the charge on the ion. So when we add the oxidation states of the nitrogen and the 3 oxygens, they should total -1 because that is the charge on the ion overall. If we think back a couple of minutes, we were talking about oxygen is usually in the -2 oxidation state. And it's always in its covalent compounds, except that one example where fluorine is involved. We have no fluorine here. So each of those oxygens is going to be in the -2 oxidation state. In total, they're going to give us 6 minuses. The nitrogen has to therefore be in the +5 oxidation state because 5 pluses and 6 minuses together are going to total the 1-, the overall charge on the ion. So that's interesting. We had a nitrogen with a -3 oxidation state in ammonia and a nitrogen with a +5 oxidation state in the nitrate ion. That's quite a big variation, and we'll come back to that in a moment. Let's look at a couple more examples. We're going to look at the oxidation state of copper in CuO and the oxidation state of copper in Cu2O. Both these compounds you may have come across. Let's think about the copper in CuO to start with. Remember, this is a neutral compound, so overall our oxidation states must add up to 0. We have 1 copper atom and 1 oxygen atom. Recall that oxygen has its oxidation state of -2 in almost every case. Certainly it's the case when it's an oxide with copper. Therefore, in this compound, the copper must be in the +2 oxidation state because the +2 of the copper and the -2 of the oxygen add up to 0, therefore giving us the requirement we require that a neutral compound must have overall oxidation states totaling 0. How about this other compound we were talking about, Cu2O? Again, the oxygen there is in the -2 oxidation state. It's just an oxide ion combined with copper. But in this case, we have 2 copper atoms. So each copper atom must have a +1 oxidation state. It's not as oxidized as the copper in the CuO. And because the coppers have a +1 oxidation state each, and there's 2 of them, that's 2 pluses to counteract the 2- of the 1 oxygen atom that is there as an oxide ion. So again, we have an element here, copper, that has shown us more than 1 oxidation state. And think about, we just talked about nitrogen has that same situation. It has more than 1 oxidation state, and actually it appears that both the nitrogen and the copper have oxidation states which are not really that predictable. They don't have one that they go to nearly all the time or all the time. And that's the case with a lot of elements. That is quite commonly the case, which is why it's important to know and to learn those common or fixed oxidation states that we talked about a few minutes ago. And finally, I'm going to leave you with some to try for yourself. Now, please do have a go at these. If you want to put your answers in the comments or you want to send me a message with them to see how you've done, then please feel free to do so. That is absolutely fine. Also, if you find you're struggling with them as well and you need a pointer, then please let me know what you're struggling with. Again, either in the comments or get in touch with me. I'll give you some contact details shortly. The ones I'd like you to try are phosphorus in the compound PCl5 and phosphorus in the compound PCl3. And then 4 compounds with sulfur in, I'd like you to calculate to work out the oxidation state of sulfur in SO2, sulfur in H2S, sulfur in the sulfate ion SO4 2-, and sulfur in the compound SF2. Don't rush these, have a go at them. Notice as well that the oxidation states of phosphorus and sulfur are quite variable too. Again, they don't have one predictable or very common oxidation state. It's important to be able to do these calculations, so please make sure you know how to do this, because this will come up. And it's easy marks if you know how, and it's not that difficult to learn really. So please make sure you're learning this to pick up those easy marks, and therefore to understand a little bit about what's going on in redox reactions, because this is going to help you to be able to understand what is going on in redox reactions, in the oxidation or reduction half equations as well. It will help you to construct those equations and help you to realize how many electrons are required in those half equations and on which side of the arrow they go. That brings us to the end of this episode. I'm going to give you those contact details I mentioned because you might want to contact me directly. If you want to contact me directly rather than just comment in the comments, the best place is going to be on my Patreon. That's patreon.com/chemistrymadesimple. You can also contact me on Instagram, and my handle there is @chemistrymadesimple. You can email me, that's matthew@chemistrymadesimple.net. Before you go, don't forget to like this episode, subscribe or follow the channel, because I've got some more coming up that are going to help you clarify the stuff that is often put across in a complicated way, in a way that isn't easy to understand. And I want you to get the best grade you can in your chemistry. Those contact details again. If you want to leave me a voice note, you can do so. That's at chemistrymadesimple.net/voice note. You can contact me via my Patreon, that's patreon.com/chemistrymadesimple. Or you can email me, matthew@chemistrymadesimple.net. And of course, if you want to know more about joining my program, where I teach you a lot more chemistry with clarity, so that you come away actually able to understand the chemistry principles and able to understand and do well in those questions in your exams, then visit chemistrymadesimple.net/program. I really look forward to seeing you there and helping you on your way to getting that grade A.